From the dawn of human consciousness, we have gazed up at the night sky, a boundless canvas of wonder, a tapestry woven with starlight. For millennia, those distant pinpricks of light were merely abstract points, their true nature and immensity beyond our grasp. Then, the telescope revealed them as suns, distant brethren to our own, countless billions forming structures so vast they challenged the very limits of our imagination. We began to understand our own galactic home, the Milky Way, as one such structure, a swirling maelstrom of stars, gas, and dust, profoundly complex and exquisitely dynamic. But understanding, truly understanding, a galaxy is an entirely different endeavor than merely observing it. We cannot conduct experiments on a galactic scale. We cannot rewind cosmic time, tweak a variable, and run the tape forward again to see a different outcome. Our universe, in its grandest manifestations, is not a laboratory in the conventional sense. And so, we turn to the most powerful tool ever devised by the human mind, an extension of our intellect and our senses, the simulation. For decades, astronomers and astrophysicists have sought to build digital twins of the cosmos, to create virtual galaxies within the silicon heart of supercomputers. These simulations are our cosmic laboratories, allowing us to explore hypotheses, test theories, and unravel the intricate dance of gravity, hydrodynamics, and stellar evolution that sculpts these colossal structures. We push the boundaries of computational power, seeking ever greater fidelity, ever more profound insights. Yet, for all our progress, there have always been formidable barriers, inherent limitations in our ability to truly capture the full majesty and complexity of a galactic system. Imagine trying to model an entire city, not just the buildings and the roads, but every individual person, every thought, every interaction, every breath. The scale is staggering. Now, amplify that complexity to the cosmic scale. Our own Milky Way galaxy, a majestic spiral, is home to an estimated 100 billion stars, if not more, each a unique furnace of fusion, influencing and being influenced by its neighbors, by vast clouds of gas and dust, and by the enigmatic presence of dark matter. To simulate such a system, with each star represented individually, has long been the holy grail of galactic astrophysics. It's a challenge that, until very recently, seemed almost insurmountable. The traditional approach to such simulations has been one of brute force. If a problem is too big, you throw more computing power at it. You add more processors, more memory, more raw computational muscle. And indeed, this approach has yielded incredible results over the years, pushing our understanding further than ever before. But there's a point of diminishing returns, a wall you eventually hit. To simulate our Milky Way with individual star resolution, representing those 100 billion stellar bodies, using conventional methods, would demand an almost absurd amount of computational time. We're talking about an endeavor that would require 315 hours of computation for every single million years of galactic evolution. Let that sink in for a moment. If we wanted to model just 1 billion years of our galaxy's history, a mere blink in its cosmic lifespan, a single simulation would stretch across 36 years of real-world computing time. Think about it, you would power up your supercomputer today, and it would churn away for over 3.5 decades, just to give you a 1 billion-year glimpse into the Milky Way's past. This isn't just inefficient, it's practically unfeasible for any meaningful scientific exploration. The energy consumption alone would be astronomical, and by the time the simulation finished, the scientific questions it sought to answer might well have evolved, or the hardware might be obsolete. Brute force, it turns out, has its limits. We needed something smarter. We needed, dare I say, intelligence. And this is where a groundbreaking innovation from researchers at the University of Tokyo has completely revolutionized the field. They realized that simply adding more computational cores was not the path forward. Instead, they needed a more intelligent methodology, a more elegant algorithm. Their solution leverages the power of artificial intelligence, specifically a deep learning model, to overcome the inherent complexities and scale discrepancies that have plagued galactic simulations for so long. One of the most profound challenges in modeling galaxies lies in bridging the vast differences in scale of the physical processes at play. On one hand, you have the small-scale, high-energy events, individual supernova explosions, the birth of stars, the synthesis of heavy elements. These phenomena occur over relatively short distances, perhaps a few light-years to a few thousand light-years. On the other hand, you have the large-scale, overarching dynamics, the gravitational interaction of billions of stars, the flow of vast gas clouds, the very structure and rotation of the galactic disk. These processes span millions, even billions, of light-years. How do you accurately represent both the intricate details of a supernova and the sweeping, hydrodynamic movements of an entire galaxy within a single, cohesive simulation? This is where the AI-driven surrogate model comes into play. The researchers employed a brilliant strategy. They trained a deep learning model on high-resolution simulations of those small-scale events, like supernovae. Think of it as teaching the AI the fundamental physics of these microprocesses in exquisite detail. Once trained, this AI model essentially becomes a stand-in, a surrogate, for these computationally intensive small-scale calculations. Instead of having the main galactic simulation compute every single supernova from first principles, which would be prohibitively expensive, the AI model can quickly and accurately predict the outcome and impact of these events. So, the larger galactic simulation, dealing with the millions of light-year scales, no longer needs to bog itself down with the nitty-gritty of individual stellar deaths. It simply queries the AI surrogate model, which instantly provides the necessary data, allowing the simulation to continue its grand cosmic dance without interruption or excessive computational overhead. It's like having a hyper-efficient specialist on call for every tiny, complex problem, freeing up the general contractor to focus on the overall construction. The results are nothing short of astonishing. Where previous state-of-the-art simulations might have represented clusters of stars as a single particle, effectively blurring the details, this new AI-powered model achieves an unprecedented level of resolution. For the first time, researchers have been able to individually represent 100 billion stars within a simulated galaxy. Each star, with its own unique properties, its own gravitational pull, its own life cycle, is now a distinct entity within the digital cosmos. And the speed up? It's transformative. That 315 hours of computation per million years of evolution has been slashed to a mere 2.78 hours. That's a reduction by a factor of over 100. The monumental task that once took 36 years to simulate 1 billion years of galactic history can now be accomplished in just 115 days. Think of the implications. What once required a career to complete can now be run multiple times within a single research grant cycle, allowing for far more iterative exploration, hypothesis testing, and refinement. This isn't just an improvement, it's a paradigm shift in how we can approach galactic astrophysics. Crucially, the researchers didn't just prioritize speed and detail, they rigorously validated their model. They compared the simulated galaxies generated by their AI with real-world observations from our most powerful telescopes, like the Hubble Space Telescope and the James Webb Space Telescope. The comparisons revealed an excellent representativeness. The simulated galaxies mirrored the complex structures, the star formation regions, and the overall dynamics observed in actual galaxies with remarkable accuracy. This ensures that the speed and detail aren't coming at the cost of scientific fidelity. The model is truly running fine, as we say, generating results that make profound scientific sense. This achievement extends far beyond the realm of astrophysics. While simulating galaxies might seem like an esoteric pursuit, the methodologies developed here have universal applicability. The challenges of multi-scale modeling, of integrating vast differences in physical processes from the minute to the macroscopic, are not unique to astronomy. Consider the complexities of climate modeling, for instance. Earth's climate system involves interactions from the molecular scale of atmospheric chemistry to the global dynamics of ocean currents and continental weather patterns. These models are notoriously complex and computationally intensive. By applying the lessons learned from this galactic simulation, particularly the innovative use of AI surrogate models to bridge scales and accelerate computations, we could unlock more precise, more efficient, and faster climate predictions. Imagine the impact on oceanography, material science, fluid dynamics, or even pharmaceutical research. Any field grappling with systems where small-scale phenomena intricately influence large-scale behavior stands to benefit immensely. This research demonstrates that AI-accelerated simulations are not merely tools for simple pattern recognition, they are evolving into genuine engines of scientific discovery. They empower us to explore frontiers previously deemed unreachable, to ask questions that were once unanswerable, and to build digital twins of reality with an unprecedented level of detail and efficiency. We stand at the precipice of a new era in scientific exploration. The universe, in all its majestic complexity, is slowly yielding its secrets, not just through direct observation, but through the ingenious application of our own intelligence, augmented by the computational power we have painstakingly developed. By building these exquisite digital Milky Ways, we gain not only a deeper understanding of our own cosmic home and the countless other galaxies across the cosmos, but also a powerful new lens through which to comprehend the fundamental rules governing existence itself. That's it for today. If you enjoyed this deep dive, hit that subscribe button. Stay curious, and keep your eyes on the skies. I'll see you in the next one.